Welcome to this lecture on stability and reliability issues in 60 SRAM cell. This is a part of module 5. So, first we will discuss the static noise margin and how static noise margin is defined and measured in for hold and read states, and then we will discuss write margin, that is the how the 60 SRAM cell is deliberately made unstable so that the write operation happens. And then we will discuss read stability failure, that is when the read operation inadvertently becomes a write operation and that results in a stability issue. And we will discuss impact of process variations on stability and how stability is even more important an issue at lower supply voltages or near threshold voltage regime. This is the 60 SRAM cell, and here we have placed two noise sources. So, here you have the output VDD. Suppose you have this output at VDD, I mean Q is storing VDD and this is storing 0. So, in that case you are applying two noise sources here Vn and Vn plus, Vn and Vn minus. So, what are these noise sources doing? So, here you are representing them. So, what are these noise sources doing? These are DC noise sources, that is DC noise. So, that is that could be because of offsets, mismatches, okay, etc. So, these kind of reasons. So, there can be a DC noise. So, what happens with DC noise? So, now what we will be doing is the experiment is you keep on increasing the DC noise value and for both Vn and Vn minus, and observe where the value stored on the cell flips. So, we can see here you have stored QB and here you have stored Q. Okay. So, in our case we are taking the example where this is VDD and this is 0. So, this is the value V in and V in prime or V out. So, what is this V in? V in is Q suppose, and this is QB. So, in that case what you are observing is that this is the butterfly curve as we had already discussed. So, this is the static transfer characteristic for inverter M3 suppose this is the static transfer characteristic for inverter M3 M1. So, suppose this is for M1 M3 and this is for M4 M6, this one is for say M4 M6. So, you can observe this small difference is because of Vn. So, you have already applied a voltage Vn to this and therefore, you have this Vn and this is Vn, this value is Vn. So, therefore, you begin from Vn, and there is some significance to these rectangles that are drawn here. We will discuss that as we go ahead. Again here we do this more carefully. So, you observe that the input voltage of Vq, suppose this is Vq and this is Vqb. So, we observe that Vq now begins from Vn not. So, here this is the complete static transfer characteristic without any noise source. So, in this we have drawn this rectangle. So, what is its importance? So, now this is the rectangle with largest size that can be fit into this quadrant or fit between the two VTCs, VTC for this inverter and VTC for this inverter. So, let us call them inverter 1 and inverter 2, inverter 1, inverter 2. So, if this is for inverter 1, this is for inverter 2. So, this is the largest square that can be fit into this inverter between the static transfer characteristics of inverter 1 and inverter 2. And what is its significance? Let us discuss. Suppose the inverter pair is in hold state, that is WL is equal to 0, that is hold state. Okay, access transistors are off and you are left with the cross coupled inverter pair. which is active. So, here you have QB and here you have Q. Okay. So, now this is inverter 1, inverter 2. So, look at this square with largest size which has been fit into the between the two characteristics. Suppose there is the value of V in because of a noise changes by this value, or VQB changes by this value. I am sorry, this will be different. This is I1 and this is I2. VQB changes by this value. So, what is the corresponding change in Q that inverter 2 would be driving? So, the corresponding change in 2 that inverter 2 would be driving would be towards this value, which is a very small value for Q. And suppose there is a change in Q, the value of Q from 0, which was at 0, to a value which is here, edge of this, one of the vertices of this square. So, what is the corresponding change in QB that one would have? The corresponding value of QB would be the corresponding tendency of change in QB. See, this is a static change. So, in dynamic case, the change would be smaller. So, the corresponding change in QB that could be seen because of this change in Q would come from I1, and that would be driven to this value. Okay. So, it is a very small change, and within the slope, see, what we observe is that the corresponding change has been for the other, for inverter 2, in the first case the change was within the range of a very small slope. So, this change in Q, this change in the value of QB would be attenuated by Q in Q. Likewise, this change in the value of Q from 0, this change would result in change in QB would result in a change in Q because of I1, which would be attenuated by I2 because you are in this region, because you are within this region. So, here it will be attenuated. So, what we observe is that the change in a noise which would be having a value which is equivalent to the side of this square which is fit would not result in loop gain which is larger than 1, and which would actually keep on growing and take the inverter pair into another stable state, that is, it would make the cell unstable. So, that is why whenever you are within this largest square which can be fit between the characteristics, you find that the cell would not be stable if the noise source Vn has a value, DC noise source Vn has a value which is equal to the side of the maximum sized square which can be fit between the characteristics. So, in the hold state of the cell, when the access transistors M2 and M5 are off, what we find is that if the noise because of any reason is larger than this minimum square, there is a chance for instability of the cell, otherwise the cell is stable. How does this matter? So, this DC noise could be because of mismatches of transistors, and in near threshold circuits or low voltage circuits, mismatches of transistors would be a serious issue because suppose there is a mismatch in the threshold voltage, the mismatch in the threshold voltage would be a large fraction of VDD, the change in threshold voltage, and that can show as a DC noise, that can be seen as a DC noise, because you can imagine that change in threshold voltage can be seen as a additional voltage source in one of the nodes. Suppose the threshold voltage of P MOSFET increases by a certain value or suppose it reduces by delta V, then you can see, suppose for I1 the threshold voltage increases by it increases by a delta V value delta. So, in that case you could have added a voltage source Vn to the gate of the P MOSFET. Okay. So, you could have looked at it as if this was having M6 transistors, M6, M4, one could have looked at this as M6, M4. One could have looked at this as an additional DC noise source. So, this can be seen as a DC noise source which has been added to the input of the inverter, inverter 1. So, now this you can relate static noise margin with this. So, if there is a mismatch of transistors or variability in transistors, it can be modeled as additional DC sources being added to the gate of the corresponding transistors, and you can look at the worst case whether that value of delta change in threshold voltage is larger than the static noise margin or not. So, in hold state you can do an analysis of this kind, and we observe that in near threshold voltages these small changes in voltage or threshold voltages would matter a lot. Likewise, now let us define read noise margin. So, here you are the access transistors are now on and you are performing the read operation. So, WL is VDD and you are performing the read operation. So, on the side of QB, that is on this side, M5 is now both BL and BLB are now asserted to VDD because you are performing read operation. So, on this side you have this equivalent circuit where M5's drain is connected to VDD and gate is again connected to VDD. So, and on this side you have this equivalent circuit similarly. So, how do we look at the noise margin now, static noise margin in this state where M2 and M5 are on and BL and BLB are both at VDD. Let us see. So, for inverter 1 the input is QB for inverter 1 and the output is Q. So, inverter 1 is this M3 M1. So, inverter 1 is this M1 M3 and you observe that for input voltage QB in, so output is VDD. But for VDD input voltage being QB being VDD, output should be, if the access transistor M2 was off, output would have been 0. But since the access transistor M2 is on and you are supposed to store 0 here, now M2 is on, M1 is on, M3 is off because QB is VDD here, QB is VDD, so M3 is off. So, in that case there is a current passing through M2 M1 that would result in, if there is a current passing through M2 M1, M1 must have a non-zero VDS. So, that is this value. When QB is at VDD. Okay. So, that is why the characteristic curve is of I1 is now looking like this. Likewise, for I2 the characteristic curve looks like this similarly. So, what does this mean? Now, if I fit this largest sized square between the characteristic curves, it has now become smaller. What does that mean? So, that is in the read state, if there is a noise of larger than this size, then it can flip the state of the cell. That is why reading stability is an issue. Now, in near threshold circuits, a little mismatch can take you to this flipping, and little mismatch in transistor threshold voltages itself can take you into the cell disturbed even while you are reading. So, that is being shown by these authors in this. Here the lightly shaded curves are the static transfer characteristics for the two inverters in hold state and the dark curves are the static transfer characteristics for the same inverters in the read state. So, static, it is being very well shown that the static noise margin in hold state is much larger than the static noise margin in the read state, and it is the read state static noise margin which would create an issue in low voltage operation. Now, let us look at the write operation. So, write is you want to deliberately make the state unstable, cell unstable. You utilize the instability of state cell and you want to flip the cell state of the cell. So, here this is Q, this is QB, and you can see it is being flipped here. Okay. So, how does this happen? So, you had Q at 0 and Q at 0 and QB at VDD, which is a low voltage 0.3 volts. So, in this case you are now you want to flip the state. So, BL you will keep at VDD and BLB or BLC in this here being called, it you will keep it at 0. So, if you keep it at 0, then since Q was 0, it is rising, and QB was VDD, it is slowly falling at a trip point which is close to the metastability point that we had discussed earlier. Metastability point. So, at that trip point, which is very close to the metastability point that we had earlier discussed, you will find that the loop gain of the back to back connected inverter is quite large. So, physically what would happen is this value is at a value which will take both the transistors in saturation, and the value of Q is also such that both the transistors are in saturation here. So, in that case both the inverters would be in high gain state and both are inverting circuits. So, that is why both would flip because of that high being in high gain state, and that is what is being observed here. Q suddenly rises and QB also suddenly falls at this point and the cell flips. This is how the write operation happens. So, here we would be interested in this trip point, that is for write the difference between the two lines should be larger than this whatever is the trip point voltage value, and with how close you take BLC, the difference to trip point voltage value by lowering the value of BLC would determine how easily you write. But what is this read stability? Now, as we had discussed, this read static noise margin is now quite small. So, if the noise value is larger than this trip point voltage value, in that case if the DC noise value because of say difference in threshold voltages, mismatch in threshold voltages is such large that it is larger than this static noise margin, and if it crosses this trip point, then while reading you would actually be writing. That can happen because BL is pulled down. Now, this is VDD and this is 0. So, BLB is pulled down from VDD and this value is also rising from VDD as we had discussed, and that is why this static noise margin becomes small. And if you somehow, if the value of QB crosses the trip point, it could also happen because of the threshold voltage mismatches. Suppose the threshold voltage of M3 reduces because of mismatch between M3 and M6. In that case, or suppose the threshold voltage of M6 reduces, in that case QB will be pulled up larger to a value larger than what you expect. So, therefore, reach the trip point unexpectedly and flip the cell while reading. So, that you can see here as you are reducing VDD, you observe that this QB trip point may be reached. See here Q and QB are quite away from each other, but as you reduce VDD you may reach QB trip point, and if with mismatches it may happen even at a larger VDD value. This can be seen more clearly here. So, here you have, this is the hold static noise margin, and with lower VDD the static noise margin would reduce this way, and with mismatch you will see the static noise margin in this quadrant is much smaller. So, this is what will be the actual static noise margin, because this is the worst case static noise margin. So, with mismatches, with reducing VDD, you can see that the static noise margin reduces, hold static noise margin. Likewise, read static noise margin also reduces. So, here the authors Calhoun and Chandrakasan have shown that this is the read static noise margin, and how it, the distribution, Gaussian distribution of read static noise margin for a large number of samples, how the mean reduces as you reduce the VDD. And likewise, here they have shown that the 6 sigma probability of the read static noise margin at 0.6 volts and hold static noise margin, which is larger, at 0.3 volts, are equal at 50 millivolts for a given cell. So, when you reduce VDD, the 6 sigma probability of failure at 50 millivolts static noise margin will be equal for 0.3 volts for hold static noise margin and 0.6 volts for read static noise margin. So, it is as if when you half the value of VDD, at higher VDD whatever was read static noise margin may now come out to be the hold static noise margin at the lower VDD. So, that is the great difference that comes about in robustness of cells, of memory cells, with reducing VDD. So, therefore, writing and reading at lower VDD is a challenge. If you want to write with ease, then reading may make the cells unstable. So, there are special circuits which would be required to assist read and write, that we will discuss in coming lectures. So, in this lecture we discuss the stability of SRAM cell, hold static noise margin, read static noise margin and write margin, and we discussed how these are impacted by reducing the supply voltage, and why these need to be considered very seriously at near threshold voltage operation. Thank you.